Greetings everyone and welcome to the Circle Post Lab. This is where we're going to actually get some meaning out of this and try to generalize some things so that when we look at circles in the future we'll know more about them. And it's a good example of what we're going to do all throughout the year with different labs. So, over the last couple of days we have taken data on various circles. We've measured their circumferences and related diameters. And then we've graphed the circumference in centimeters versus the diameter in centimeters, and we found that we got a linear graph. We know it's linear because the correlation coefficients that we got were very near to 1, 0.99 somethings generally speaking. And not only that, but they also went through 0, 0. Well, there's something special about a relationship when it results in a graph that is linear and contains 0, 0, when both of those things are true. Think about it. In order for a graph to be linear, if I were to double the diameter, what would have to happen to the circumference? Well, if the graph is going to be straight, if I double one, I have double the other. If I have a circle with 3 times the diameter, it would have to have 3 times the circumference. In other words, the two variables change the same. What do you call that? Well, that is called a proportionality. And we can write that thusly. This would be read as the circumference is proportional to the diameter. Notice here that we're using symbols. Again, it's using mathematics as our language. C stands for circumference, D stands for diameter, and this little squiggly thing in here, which looks like an infinity sign that's opened on the right side, is a proportionality symbol. So again, circumference proportional to the diameter. And that's a very powerful realization because now we know that if we compare two circles to one another, however the diameters compare, the circumferences have to compare the same way. If the diameter of one circle is half as big as the other one, then the circumference would be half as big as the other circle. But it doesn't yet allow us to make direct predictions. This diameter results in this circumference of a circle. For that, we need something more powerful. We need a math model. In other words, we need to turn this straight line into an equation. Well, we know how to make the equation of a straight line. We use our old slope-intercept form, the slope-intercept form of a straight line, which is y equals mx plus b. So let's make one now for this graph. Y is the y variable, the variable we're graphing on the vertical axis. That is circumference. So as a symbol, we're using c. That equals m, which is your slope. Now before I actually throw the slope in there, you have been entering your slopes into a Google form, and so I want to take a look at that Google form. This is actually for 4 hours of honors physics, as you can see, in 2013. And here are all their slopes. There's 34 data points. And they average out to 3.10297 and so on, or about 3.1 if we go to a couple of digits. All right, so that's kind of the class average here. And so that's what I'm going to use in my presentation from now on. So our slope would be 3.1. Now remember that in here we need to have units with our numbers so that we can understand what they mean. The units from a slope come from how we find slope, rise over run. So the units of rise are centimeters, and the units of run are centimeters. So our slope is roughly 3.1 centimeter per centimeter. Well, here's a question you don't get asked much in math class, which is, what does that actually mean? And I don't mean what does it mean on the graph. You go up 3.1 and over 1. I mean, what does it physically tell you about circles? Well, if you think about this, a slope is how much the vertical variable changes compared to how much the horizontal variable changes. And so what this would mean is, for each additional 1 centimeter of diameter, the circumference increases by 3.1 centimeters. You get 3.1 centimeters of circumference for every 1 centimeter of diameter. So it's telling you how much the circumference increases for a change of diameter. So slopes always tell us how much one variable changes with a change in the other. So this is a very powerful thing now, because now we know that there's this basic thing about circles. Right? We know that there's a relationship there, and once we finish the equation, we'll have a good predictor. Now, one thing you'll notice is that we have centimeters per centimeter. So technically those units cancel, and you're left with 1. Of course, you don't have to multiply by 1, So this is going to be one of only a very small handful of numbers, sometimes called coefficients, that will have no units associated with them. However, to really understand what that number means and where it comes from, it's helpful to remember the lab. And this is why doing the lab is so much more powerful than me just telling you what that number should be. So we've got our y and our slope, so now we need our x variable. Well, what we graphed on the horizontal axis was diameter, so that's a capital D. The last thing we have to decide about is the y-intercept. And is that y-intercept significant, or can we just call it 0? Now you probably got some sort of y-intercept from LoggerPro. So there's two ways we can analyze that y-intercept. One is the test of logic, and that means what would it actually physically mean if there's a 0, 0 point on the graph? I don't mean mathematically that it would go through the corner. I mean, what does it mean on a graph of circumference versus diameter for there to be a 0, 0 point? Hopefully you can see that what it means is if the diameter of the circle is 0 centimeters, the circumference has to be 0 centimeters. Now that makes good logical sense. And if you have a teeny, teeny, tiny, no diameter circle, then you have to have a no diameter or no circumference circle as well. So logically, we shouldn't have a y-intercept. However, we did get one from the LoggerPro, and that's, shows that we have a little bit of error. Now, the question then is that error so big that we need to keep it? Or can we just kind of say, you know what, close enough, let's just call it 0? Well, I have taught you in the past to use a quick little, not great statistical analysis called the 5% rule, but it's a good rule of thumb for us to use at this level of physics. It says, again, if the y-intercept is less than 5% of the maximum y value, that's the circumference, it can be considered negligible. So, the maximum circumference value was around 74 centimeters, give or take a few. 5% of that is 0.05 times 74 centimeters, which is 3.7 centimeters. Hopefully none of your y-intercepts were anywhere near that. I think the biggest I've seen is, around a 1 or a 1.5 centimeter. So it's not anywhere near 5%. So we're going to say it's so small, let's just say it's negligible, and it's a 0. And since you don't have to add zeros, there's our math model. The circumference of every one of those circles we measured is equal to 3.1 times the diameter. Now, that's probably a familiar kind of equation to you that you learned in math class. And so let's talk about what that slope is really supposed to mean. Right? And what is it really supposed to be? Hopefully you're noticing that it looks like a number that you know. And that special number we call pi. That's the way you write it in Greek. And that number is usually given to a couple of decimal places as 3.14. Remember, ours was like 3.10, right? So pretty close. So we can define pi now as the slope of a graph of circumference versus diameter. This is where pi comes from. Right? Pi is the ratio of the circumference to the diameter of any circle. It's not just some random number. It's a number found in nature. It's a very powerful number. Right? And it's usually associated with things that are circles or that move in circles or that have circles associated with them. And so we see pi in those situations. And whenever you see pi in an equation, it's usually got something to do with circles. Right? And so we can now define pi. And we can take that pi and put it in for our 3.1 to make this a little more general of a math model. Right? And we get circumference equals pi times the diameter. Now, we can also do this just quickly. Nice thing to write about in your lab report, just to see how much error we have. Take your value of pi and compare it to the value of pi that we know and love, 3.14. My guess is that as we did with our 3.1, I mean to one decimal place, we don't have any error, right? 3.1, 3.1, and even to two decimal places, right? We were only off by 0.04, and that's only 1% or so of error. So this is, even though we did this lab just with measuring tapes and that, it's actually a pretty good number. Pi is actually a good experimental number. So this is what we call a general math model. So next time we come to circles, later unit when we talk about things that move in circles, we'll be able to pull out this equation and we will know what it is and where it comes from. Now, one other little thing with pi. and circumference and diameter. Oftentimes this equation for circumference isn't written in terms of diameter, it's written in terms of radius. Radius is of course denoted by a lowercase r, sometimes a capital, and it's the distance from the center to an edge of a circle or sphere. Now, as hopefully you know, right, a diameter is 2 times the radius. So if we plug that into our general math model, we now have 2 general math models. We can say that the circumference is pi times the diameter, or the circumference is equal to 2 pi times the radius. These were equations that you probably knew, but you may not have actually known what they meant and where they came from. And now, hopefully, after doing this lab cycle, you do.